So now we're going to start taking a look at how we actually implement some of the sorting algorithms that we've seen so far. Now, before we actually see an implementation, I want to take a few moments to discuss what our strategy is going to be for writing these sorting methods. So the first thing is all the sorting methods we write are going to be public static. Public because we want anybody to call them, and then static because there's no reason for any sort of object to be instantiated to call these methods. These methods work on objects that will pass as parameters. So we'll have public static as the modifier to our method. Then we're going to sort these arrays in place. So there's not going to be a return. Whatever array we pass to the sorting algorithm is going to be sorted, and then we'll modify that array. We're not going to create a new sorted array. We will be changing the array that gets passed in. So the parameter is going to be a generic array, and so we add that to our method signature. Now notice it's a generic type t, which means it's going to take any object. However, while t is generic, we still want it to be some class that implements the comparable interface so that we're able to call compare to. That's going to be how we compare objects in the array. So instead of just making this a generic method, we're going to say it's generic, but that generic type extends comparable. And all of the sorting methods we write are going to follow this form, where instead of saying sort algorithm, we'll actually put the name of the sorting algorithm. Now we also want to be able to sort some part of the array, not the whole array, but some subarray. So we're going to overload the methods so that we have one that contains the min and max indices of the subarray we want to sort. So here we just have the whole array, but then we can add min and max parameters to say, hey, sort in between these two indices. So to review, we're going to have two methods for each algorithm. We're going to have a method that takes an array as a parameter. That's going to be used by the client, typically. And we're going to have a method that takes an array and an index range for use by other methods. And we'll use this also with things like recursion, or there are cases where maybe some algorithm is faster than another once we reach a certain size, and so we may want to switch to a certain algorithm. And again, since we're sorting these in place, if we have a recursive method, by passing in these min and max parameters, we don't actually have to make new arrays each time. We just say, hey, here's the part of the array that you're going to sort. Okay, so our first sort that we're going to implement is our selection sort. So let's take a look at our sorting class. Recall that we have the helper methods that we're going to use to do comparisons between two objects and to swap two objects in an array, and also our test methods that'll tell us if an array is sorted. So now let's create our selection sort. I'll actually start off by just writing the signatures for the two methods. And I'll copy and paste this for the overloaded method. Okay, so here now I have my two method signatures, and you may wonder, why is this on two lines? The only reason is because if it was on one line, it would go way out there and get kind of hard to read. So on the first line, we have the descriptors for the method. The second line, we have the return name and parameters. And again, that's just to make it a little bit easier to read, hopefully. So let me add a space here. And for this selection sort, it's actually going to call the helper method with 0 and the length of the array as its parameters. So we're going to call selection sort, and we want to run it between 0 and data of length -1. Those are the two indices we want to sort between. Again, those indices are inclusive. We'll actually be implementing the logic of selection sort in the overloaded method. So let's take a look at how selection sort works, just as review. So with selection sort, we have some array, and the way it's going to work is between min and max, we're going to start at the first element, and then we're going to find the smallest element in the array, which in this case is 1. And then once we do that, we're going to swap 1 with whatever that next element that we're looking at. So we swap the 9 and the 1. And now 1 is the smallest element in the array, and so then we move to the next element. Now here we're looking for the second smallest element in the array, and then the third and fourth, and so on. And we'll continue to do that until we reach the end, at which point the entire array is sorted. Since this is an array, we're going to keep track of the elements using indices. We're going to want to keep track of the index of the smallest element in the rest of the array. And of course, that'll be the smallest index in each pass, and it's the smallest value, not the smallest index. Keep that in mind. And since we don't know who's going to be calling this method, we're going to make sure that the min and max values are always valid. So if you give us something outside the array as your min and max, we're going to make sure that we change those so that if it's beyond the end, we give the last element. If it's before the beginning, if it's negative, we'll start at index 0. So now let's start with the actual logic of our sorting algorithm. So we're going to start at the minimum. We're going to go to max, and we'll increment each time. Now, as a reminder, next is the starting point for each pass, so it's the index where the next smallest element in that pass will go. And of course, as we move through the array, next will increment because we'll found the first smallest, so now we're looking for the second smallest. Once we find that, we're looking for the third smallest, and so on. So we'll set the index of the smallest equal to next, because that is the index of the smallest element we found so far, wherever we're starting. And then our next for loop will scan through the rest of the array, starting at the index after next, because we're going to compare that index with the previous index, which is going to be next. So now we'll check to see if what's stored at index scan is less than what's stored at index of smallest, and if what's located at scan is smaller, then we'll set index of smallest to be that location. So that way we're keeping track of where the smallest element is located in the array after each comparison. So now, once this loop is complete, we can go ahead and swap in the array whatever the index of the smallest element we found was with the element stored at index next. So again, next is where it's going to go. Index of smallest is that new thing. And of course, whatever was at index next, we just put into the array somewhere, and we'll deal with that on the next scan. And that concludes our selection sort method. So we can test this in the sorting tester. And so that will guarantee that inside of here, we're going to run it 500 times and make sure that our array is sorted. And as you can see, that it takes the unsorted arrays and sorts them correctly. Okay, so that's selection sort. That's our first sorting algorithm. And hopefully that gives you an idea of how we're going to be implementing these method-wise. For the simple sorts, insertion sort and bubble sort, which will be next, they work similarly. The only difference is really what goes on in this loop. So we'll see another video with those, and then we'll also see how we implement our efficient sorts, merge sort, and quick sort.